So good afternoon. My name is Amrinder Nair. I'm in mechanical engineering. The onset, I would like to thank ICTAS for the support. So this is a project we are dealing with, is determining material constants of nanofibers. So we're really interested in the material structure, how it arranges when you start making nanofibers. So nanofibers which we are defining are anyway 200 nanometers or less. How do the mechanical properties, material properties like Young's modulus, tensile strength, elongation at break, how do those change? And how do the molecules arrange themselves in the fiber? So these are very important properties to be determined to advance biomaterial scaffolds, smart textiles, advanced materials, and so forth. So the objectives of our project were, from the outset, using STEP, which is a spin rate-based tunable engineered parameters technique. It's a fiber manufacturing platform. It's a non-electrospinning platform. It gives us the capability to deposit fibers anywhere from sub 50 nanometers in diameter all the way up to microns. All the fibers shown out here in this study are at least millimeters to centimeters to inches in length. We can make fibers which are 10 nanometers in diameter, but which are only about a micron or so in length. We do not know where to use them, so we don't include them in our studies. So the objectives, first of all, the co-PI for this is Bob Moore, and he came in from the polymer chemistry, polymer physical chemistry aspect of the things. So the objectives outlined were identify and develop appropriate boundary conditions to study material properties using dynamic mechanical analysis and X-ray scattering methods. So we wanted to look at, are we getting for an amorphous polymer system like polystyrene, when you start making fibers which approach 100 nanometers or lower in diameter, do you start seeing short chain ordering at single fiber level? 100 nanometer fiber you can't obviously see optically. So the big challenge out here is how do you go about applying boundary conditions to them? And can you use existing tools to measure the orientation of the chains? To our dismay, we found that we cannot use DMA, obviously, at the single cell level, so then we started making braids of fibers. For example, shown out here, these are braids. Each braid consists of approximately 30,000 fibers or so. So we made braids with differing twist numbers. So if you increase the number of twists for the braids, obviously the mechanical forces increase. What we found, which was very interesting for the first time, was that beyond a certain number of twist angle, the internal structure of the braid was very different, and that led to the decrease in the mechanical property. So the braids were internally fusing together, and thus there was loss of mechanical property. We could not get, not shown out here is our attempts at DMA and the X-ray scattering. We are still working on developing those techniques to look at single fiber and also braids of fiber. The second part of the project was develop an integrated approach to characterize a single fiber for its mechanical properties. So as shown out here, play this movie for you, though. So what is shown out here is an AFM probe, and this is a TEM grid, and this is a single fiber that is suspended across the TEM grid. I come with the AFM in the lateral mode, and at different strain rates, I can break the fiber. So this is done approximately at around 10 to 20 microns per second, but you can see that the boundary conditions here and here are maintained. So the fiber breaks with near exact clamp boundary conditions. And we have demonstrated that we can take this fiber and really scale it down to nanoscale. So this would be a plot of the diameter and the breaking voltage from the AFM to break individual single fibers suspended onto TEM grids. And the insert out shows that we have done, the smallest diameter fiber we have broken is around 30 nanometers in diameter. We are improving on this technique to get down to even smaller diameters. The problem is that the current AFM systems, in the lateral mode, they have a lot of noise. They're not in closed loop control. So the voltage required to break this fiber at the nanoscale gets embedded in the noise signal of the AFM. So if you can have like a closed loop control in the LFM, that would really help us in determining the exact voltages required to break single fibers. The very interesting thing that we also observed from this was that you can have two different ways in which you can break the fiber. If you go very slowly, the fiber deforms plastically, and it will keep on elongating, and it will actually not break. At very high strain rates, the fiber instantaneously breaks. So that's what we call it as an elastic response. And you can't see it probably out here, but this would be a fiber that broke elastically. And these individual little ones that you see out here are plastically deformed fibers. The next interesting thing we saw at high molecular weights was slippage occurring. So this is a fiber, this is the original diameter, and then when you apply a deformation in the lateral mode, you see this tube formation occurring. So this we think is that the chains inside the fiber are slipping. And that is also a function of the strain rate and also the molecular weight. We don't see this at low molecular weights. We don't see this in PMMA. We see this in polystyrene. So we want to examine this more in detail. So our planned experiments are that we want to keep the same number of molecular entanglements, have different molecular weights. That way we get we get fibers of same diameter for different molecular weights. Now you want to come and break them. Then it will give you an idea on the effect of molecular chain on the tensile strength of the fiber. So the third goal of the project was to develop isodiametric design space and hierarchical assemblies from that. Isodiametric, by the word itself, isodiameter is lines of constant diameter. So we developed this platform in which these vertical lines that you're seeing, they're ranging from 80 nanometers all the way up to 800 nanometers. So these lines are lines of constant diameter. So this is a chart that shows molecular weight and the solution concentration. So if you have a molecular weight of polystyrene, say 1 million, and if you want to deposit a fiber diameter of, say, 100 nanometers, what is the design space that you need to choose? So you can come across the 100 nanometer design space and intersect it with the 1 million molecular weight, go down on that, that gives you the solution concentration required to form 100 nanometer diameter fiber for 1 million molecular weight polystyrene. So this is a very powerful tool. This is not there currently in any of the polymer journals or polymer literature. By just looking at the chart, you can explore the design space. Now you can extend this to 4 other polymeric systems. So we have extended this to encompass PMMA, polyethylene oxide. This would be another chart for polyethylene oxide. We are currently doing experiments with polyurethanes, PLGA, which is polylactic glycolic acid, PLA, and so forth. Now, having the ability to deposit fibers with very controlled diameters gives you the unique ability to develop hierarchical assemblies. Hierarchical assemblies are in single layer, multiple layer. So as shown out here, we can have fibers of 200 nanometers spaced apart, 500 nanometers and 2 microns and so forth. Then these are in single layer. Now you can go and deposit fibers at user-defined angles. So for example, these are at 15 degree, 30 degree, 45, 90 degrees. To improve that even further, you can have unit area spaces. Like shown in this image, you have one area and the second area, and this is a very repeatable process. The idea of hierarchical assemblies is now you can put together 12, 20, as many layers as you want with desired properties and porosities, so you can seed cells into them and develop possibly a tissue model. Then the next thing we explored was developing or achieving control on the surface morphology. So this would be on the left shown smooth fibers, and when you cut them, you look that they are solid fibers, but then controlling the solvent volatility and the relative humidity, you can induce surface features such as pits, and you can start making tubes. And then you can also have fibers with multi-channels inside them. So you can control this repeatedly. So I've been able to achieve that. Then the next thing we did was we took the same tubes, we put carbon nanotubes inside them, and we did stress-strain curves. And as shown in this curve, the carbon nanotubes with the PS are a lot stronger. Where do you apply all this? One of the applications we are looking at is understanding single cell behavior. What is the elasticity of a single cell? If a cell spreads, if you can control the spread area, does the cell modulate its elasticity? So currently we are doing experiments in which we are looking at cell morphology as single cell spindles with different angles, and then we want to come with the AFM, deform it, and get local elasticity maps. So that gives the objectives and where we have made progress. We have had several publications come out of this project, notably Polymer Journal from the Nature Publishing Group, Soft Matter, Journal of Inorganic Non-Metallic Materials, and New Journal of Chemistry. We are in several rebuttal process, Langmuir, Acta Biomaterialia, and Integrative Biology. These we hope will be accepted soon, and then one of the papers is under preparation. We have submitted proposals to NSF and NIH. We are pending 2 and 2.4. We have made several presentations at BMES, AICHE, ASME. We have had, 4 Best Student Awards at the conferences.